In this video, I'm going to demonstrate 3D interactive scatter plots in Loon. In Loon, we affect that by the L_plot3D function, which is just like a regular scatter plot with the exception that it's got an extra coordinate, Z. So that'll allow us to show the points as a 3D point cloud, which we can rotate around interactively. The rotation is achieved by just toggling the R key. It turns it on or off. Rotation can happen vertically around the vertical axis using the left-right arrow keys, or around the horizontal axis using the up-down arrow keys, or alternatively just freehand with the mouse, just picking up the point cloud and moving it in the direction you'd like it to rotate. Some things to note as we're going through the demo. The origin of rotation will always be identified by a set of 3 axes at the center of the plot, and you can always change that origin simply by using the panning operation in Loon, which allows you to move the point cloud to wherever you'd like it to be, nearer or farther away from the origin. The 3 axes themselves are colored to give you a clue as to which was which in the original coordinate system. So X will be red, Y will be blue, that's the horizontal and vertical in the original position, and Z will be green, which was orthogonal to the screen in the original position. As the points rotate, the axes will move in with the rotation, and when the axes appear to be entering into the screen, going out through the back of your screen, they'll darken. As they're coming out towards you, they'll be light. That'll help give you some orientation as to how the point cloud appears compared to its original position. When the plot's not in rotation mode, any sort of thing, action that's available from Loon will be available. Right, so let's get started. So for the demonstration, we're going to look at 2 different data sets. First will be a large protein molecule, a human antibody, human immunoglobulin G1 or IgG1. That'll be a data set that'll be available within the loon.data package when that becomes available. The other is a data set that's available in R right now, and so you can use that right away when you install Loon. That's the Quakes data. So the first data set is an antibody molecule. It has about 10,000 atoms. We're only going to look at about 1,500 atoms, which are the alpha carbons that define the geometric structure. All the other atoms associated with the molecule will be amino acids or carbohydrates, which will be hanging off these alpha carbons. So the data we have will have the spatial coordinates according to model and X-ray diffraction measurements to locate the atoms geometrically, and we'll have some other information available, such as what amino acids or residues are hanging off each atom. So the script that we're going to follow, and you might want to just pause this and read this over at your leisure. We're principally just going to read the data in, plot the molecule in 3D, play with that a little bit, focus on some subset of that molecule just to show you some of the features of 3D plot rotation and the interaction within Loon. And I'll have some scientific interest as well, noticing the residue structure. And then back out and look at all of the atoms again, all 1,500 plus atoms that we have available, and look at the symmetry of the whole molecule, particularly as it relates to the residues or amino acids or carbohydrates that are hanging off the carbon molecules. Finally, we're going to look at identifying the chains. That information is also available in the data set. The carbon chains, we have the sequences, the light chains, the heavy chains. There are 2 of each, and we'll follow those sequences by linking through brushing with a 2D scatter plot. And just for the heck of it, if you ever find a view of the data that you like, you can always print it. Okay, that said, let's go off to the demo. Okay, so here we are with the demo. Here's the data. We'll just read in from a CSV file. As I said, it'll be available in a loon.data package a little later, and put that data together just using dplyr when inner join. So what we have is a data set that looks something like this. Record type, we have the name of the atom that's the residue, which is typically amino acid, what chain it belongs to. There are 4 or 5 of these chains. And of particular interest, of course, are these 3-dimensional coordinates, the X, Y, and Z coordinates, which allow us to position every one of the 1,500 plus molecules in the alpha carbon. So let's do that now. So to plot the molecule in 3D, you want Loon, and now you want to have the model itself, and I want to save that onto a variable G1 here, and which is got mixed case here because this will be the plot, this is the data set itself. And we're going to do Lplot 3D, which just looks like an L plot. The only exception is we've got a Z here, which gives us the third coordinate that we're going to use in 3 dimensions. The rest of this will just be stuff that will make our life a little easier in the demonstration. It's not necessary, but it's some choices that you might like to make. So when we execute that, we get the inspector comes up, and now the 3D scatter plot, which will appear here. And you see I've got no axes or anything around it. I have show labels equals false here, so we're not seeing much in that way there. And it's reproduced over here in the inspector in the world view, which allows us to interact with the plot that we're focusing on. Okay, so bringing this plot to the top here, I'll select R. Now it's in rotation mode, and you see I've got a little flag here, rotation mode, so that you know whether you're in rotation mode. I can rotate that around the vertical axis, here the y-axis, this blue axis, or the x-axis, this red axis, with just the arrow keys. So left, right arrow keys, I can rotate it around the vertical, and you can see some of the structure that's appearing there in the carbon atoms. And I can rotate it with the other arrow key around the horizontal and get a little more information. Alternatively, just freehand, I can just grab this and move this around to whatever position I like. And as you get a little practice this, you get a little better at making these kind of moves. So that's freehand rotation there. If I was lost, we can go back here in the little coordinate system here, the axes. I can put it back in the original position just by clicking on that. So we're back in the original position now. So let's focus on these blue atoms here, which I happen to know are the carbohydrates, or the carbon atoms that have got the sugars hanging off them. And I'm going to select the black ones because I don't want those. I'm going to select those. They'll all appear as magenta, and I'll deactivate them, that is cut them away temporarily, just remove them. This allows us to see the relationship between the point cloud that we have remaining and the axis system. You see it's nice bright red and blue, and as I pick this up and move it around, you see that's the center of rotation. And as I move in, the axis moves into the screen, it gets darker. When it comes out, it gets brighter. And so I can move them all in, and they'll darken up. And again, this may be not where I want the origin, so I may want the origin to be in the center of the data. With the right button on the mouse, I'll just pick this cloud up and move it over. And at least in this plane, I've got it centered, but I may not be centered as I move into the screen. So let's just move this again. Yeah, I'm off a little bit, so I'll move that down. Rotate around, not bad. So I'll get that to be the center of rotation. Oops, I was moving it there instead of rotating. So there's the left button, rotate around. Right button will move the points. So you can see the structure there already. I can zoom in on this with just scrolling. Have a better chance of seeing that structure centered there and move it around. You see it's got lots of different arms, lots of geometry in these set of carbohydrates. So you might wonder, what are all of these different atoms, these group of atoms that appear? Looks like some symmetry or some mirror symmetry of some kind. So what we're going to do is, I just want to mention I could hide and show the labels here. So over here with just showing the labels, if you wanted to, that'll give you the coordinates that we're currently looking at on each of the labels here, and of course the title that we gave to the plot, so that you could see what linear combination each one of these axes currently are. I'm going to turn those off because they're not that interesting when we're looking at this atom. So each atom, as I said, is a carbon atom, and it's got hanging off at a residue, which will be an amino acid, or in the case of the particular atoms we're looking at, will be a sugar. So what I'm going to do is look at the residue. So I'm going to color every atom in that whole plot by what residue it has. I don't know how many residues there are, but each one will get its own unique color. When I look back at the 3D scatter plot, sure enough, I see there is considerable structure here. There are all these blue guys appear at opposite arms. Looks like a bit of a twist in it, and the green are on opposite arms again with a bit of a twist. But there's an awful lot of symmetry in this structure in the carbohydrates here that is pretty obvious now. You might wonder what those actually are. I'll go over here to the inspector and turn on item labels. We constructed this with a long string at the beginning when we created the plot. And now when I hover over a point, you'll see it'll pop up. So these blue guys are galactose, or the residue abbreviation GAL, GAL. So those are the blue ones, and same over here, they'll be the same thing, galactose. These green ones are fucose, and you can see they're in the chain ID. See, the purple is NAG, NAG is the residue. The orange ones, MAN, MAN, are for mannose. So you can see the structures that are there given by the colors. So those are the residues that are hanging off the carbon atoms, and that's kind of interesting. It's a very nice, close collection of colors inside this carbohydrate group. So what happens if we bring back all of the atoms? So bring back all of the atoms down here. You'll see it just by having setting the active to be true for every point in this cloud. When I do that, they will all come back, and they'll all come back colored, because that's what they were. So now we can see the colors of all the amino acids that are hanging off them. It's purple here, that's serine there, so it's a little slightly different color purple. And these are no longer sugars, these are all amino acids that are hanging off, but we may want to see where we're at. So let's again get this plot back to position and scale the whole thing to the plot. So there's our entire molecule. This is the carbohydrate region we explored earlier. I'm going to turn off the item labels so they stop popping up. There's this the amino acids, the sugars around the carbohydrate region we were looking at before. But even here, you can still see the symmetry of the colors on either side. There's a lot going on, a lot of structure in this atom, in this typical T-shaped antibody, by the way. And as we move this around, you can see the beautiful symmetry here given by the colors. And again, those are the colors indicate which amino acids or which sugars, in the case of the carbohydrates, are hanging off. This little area is called the hinge inside here. So let me put this back in place. Okay. So one way to see a little more structure here is to have a look at the another plot. We noticed that we know that there are chains. So the chains are identified here. They're either the H chain or the I chain or the L chain or the M chain or the C chain. And the H and I chains are heavy. So I'm just going to get logicals here telling me which observations are in the H chain, which observation in the I chain. And then I'm going to color everybody that's in the H chain will be gray. Everybody that's in the I chain will be light gray. And similarly for the light chains, L, M, color that. L will be royal blue, the M chain will be light blue. And the remaining chain is the carbohydrates we saw before. I'll just make those pink. So so we can see the chains better. I'll increase the point size. And now there's our figure, and you can see that you can sort of see that the points chain together. If I shrink these towards each other so that the atoms look like they're touching, you can get a better appreciation of the chain structure. You follow any one of those colors and you can see the chain that's going on as it crosses over through the middle. So the heavy chains being the dark gray and the light chains being the light blue and the dark blue. They're clearly identified with different parts of the atom. It might also be easier if we just look at one of these chains at a time, and that's easy to do. Again, we could do all of this by the way just by selecting up here. So if I select the dark gray chain, inverted, make everybody else go away, deactivate. So now I've got that one chain by itself. Alternatively, I could have done this programmatically down here. This is the H chain or the I chain in this little command here, and I'd have both of them appearing here. So I have both chains appearing at once. So let's just leave it at that for the moment. You can see that again, the chaining of the atoms. You can do that for any set of the chains if you like. So let's just look at the H chain alone. So that's a dark gray chain, the heavy chain. And now I'll have another, just a plain old two-dimensional scatterplot, no 3D here, looking at the residue sequence number and having this in the same linking group. So I'm going to get another plot here. It's only showing the heavy chain, so it's just got one set of residue sequence numbers and one chain ID. But the interesting bit about this is if I look at it and down here I actually brush this. If I brush this, you can see that I'll just go along in the sequence of chain, and you can follow it up in the molecule at the top. And you can see that how that chain curls back and forth on top of itself. I'll make this a little narrower, narrower like that, so we can get a better, shorter piece of it. And you can see that chain moving through the 3D molecule. Let's move around. You just cross the hinge there, down to the bottom part. And you can do that for any one of the chains. And supposing that you found some bit that you wanted to highlight, that picture there, I could just take a snapshot of that using just the plot function in Loon. So plot IG-G1, now that gives me a grid graphics version of this that I can export, play with. It's just a nice grid graphics that I can make a picture of. Okay, back to the slides. Right, so that was the antibody, the human immunoglobulin G1. The data set that you have access to immediately with Loon is in the Quakes data in R. It too has got physical three-dimensional data. And of course, data sets the dimensions don't have to be physical. It's just convenient and easier to understand for a demonstration if they are, but they can be any set of three variables. But we're looking at longitude and latitude and the depth of an earthquake, and these are degrees of longitude, degrees of latitude, and kilometers of depth. So we have to do some kind of scaling to get them all in the same box. We've got other information. So the script here before, I'm going to begin with a 2D plot of the longitude and latitude to see where the earthquakes are, and I'll put the islands on top of it so you can get some sense of where in the globe we are. Then we'll look at the 3D plot and rotate that around so we see the depth appear. We'll just use the arrow keys for that. And again, note that we'll be rescaling the quakes. Having done that, we'll have a look at some of the geophysical properties that the geophysicists observe in this data set, performing essentially the kind of functions we are doing now, although they didn't have access to a 3D point cloud rotation at the time, I don't believe. But they could certainly slice through the data with static plots. So on the 2D plot, we're going to do some brushing to identify some interesting features in the 3D plot, and we'll do that twice. So let's go to the demo. Let's get rid of the molecule. So quakes data. Again, we've got the quakes, library Loon, and now I'm going to do all of the quakes here with longitude and latitude and some other information. Producing a linking group called Quakes now, showing guides, and I've kept the labels on here. So I've got the earthquake locations there. Each one of these circles is at one of the 1,000 earthquakes that we have available. I'm going to add some maps to this. Do that. So here, going to the World 2 maps, I'm going to select off these islands which are nearby the earthquakes. Don't plot them, just get the coordinates in the NZ Fiji map. So take this New Zealand Fiji map, and in Loon I'll layer it on top of the plot P, color it light green, and in other videos I'll show you more about layering. But you see that I've got the islands here, and you can see in the world view that there are other islands that appear off. And if I zoom out on this and move it around, I'll be able to see where we are located with New Zealand down here and Fiji up here. So that said, now I need to get a 3D plot. So as before, this is plot 3D with longitude, latitude, and depth, but I'm going to scale this so they're all in the same box since I'm dealing with things on different scales, on degrees of latitude, and longitude, and then on kilometers of depth. So just to put them into a 3D box. So, and assign that to P3D. So there we go. Looks a lot like the previous one, except this plot is now 3D. So I can, for example, put in rotation mode here and rotate down. So I've got depth. I'm keeping the coordinates there. Again, I'd like the depth here to get to be -1, and I'd like that latitude to get down to 0. So let me just see how close I can get to that. Yeah, 1 and 0, perfect. I'm a little bit off the page here. Right button, I'm just going to move these guys up. And there they are. Great. So the geophysicists focus on this part, the Tonga Trench part of the data set. So I'm just going to take this part for the moment and remove this. So deactivate that and move this over so I get a better sense of what we're looking at here. And now on the 2D plot, I'll begin with brushing. Let's see, a brush here, and I'll get a skinny brush, flat brush, so I can go from north to south through the data set, just like that, and see what's going on over here in the 3D scatter plot. So if you'll notice that I've got essentially longitude along here, so this is still the same X structure as before, but now I've got earthquake depth, with the deeper ones being down at the bottom and the shallower ones being near the top. So as I move down from north to south, you'll see that I'm picking off points here, and they seem to be falling on that diagonal kind of line we see across there. And that kind of structure continues and shifts from east to west. Here in the longitude, again, a diagonal here, that magenta. And let me see, if I wanted to make this more obvious, I'd select everything and let's make them all blue. So now the magenta will be easier to distinguish. So now you'll see the diagonal appearing there. As we move from north to south, that diagonal just moves across the plot. And the geophysicists point out that this is with the one plate being subjugated by the other in this region, that what's happening, there's a shearing effect. So this is evidence of a shear. Make that a little narrower. So you can see that nice, fairly consistent shear happening. Okay, that's the first thing that they notice or they point out in the Nature paper. And it's I believe 1984 Nature paper. The credits will be given at the end of the last slide, so you can actually check it yourself. Next thing I want to focus on is they're going to focus on this hook. You see this little question mark that appears there. So I'm just going to select that and hold the shift key down so I'm selecting multiple selection here. Just get that hook there. Then that's what I want to concentrate on, so I want to cut away everything but that. So I'm going to invert this selection, get my brush out of the way, and deactivate that. So all I've got left is the hook now. And now I'm going to zoom in again on this. You see there's sort of breaks into pieces. There's a northern part, a central part, and a southern part. And the authors certainly look at these separately. And over here, I'm going to just pull this into the middle and rotate that this way. So just about the vertical axis. And I guess that will do for the moment. Here are the features that are being observed by the geophysicist. So we look in this northern part. We got this nice vertical structure here, indicative of again a shear. Let's go to their words here. So this is lineation is a shear failure. So that's this color here in the northern part. And then the central part, when I go across here, you see I've got, again, kind of a vertical there, and then sort of a horizontal happening here, this kind of L-shaped. And they describe this as a shearing and an out-of-plane shearing. And then there's this gap region here. We've got a gap between the two sets of data. And on the southernmost region, we've got more kind of a vertical shearing, again, another vertical stripe here in this direction. So we have a few vertical lines here that appear on the southern region that they describe as one thing happening. The northern region is very similar to the southern region, these vertical structures. And in the middle, we've got this, as they say, out-of-plane shear. And let me go here and rotate a little bit. Out-of-plane shear and shearing effects. We've got that vertical column and then this kind of angular column. So that provides the geophysicists with a fair bit of information about these deep earthquakes and what that has to say about the plate tectonics. So back to the slides. Right, so that ends the demonstration. I just want to give you the sources of the data so you can go check it for yourself. You can find the data that I have here at the UMass website from Eduardo Padlan. He still has that data up. It's from 1994 paper. And I picked up the names of the amino acids and the sugar molecules that are off the carbohydrate chains from this source. And the quakes data are the deep earthquakes. It's a subset of 1,000 earthquakes from those 5,000 earthquakes that the authors of the Nature article here back in 1984 had gathered. In the R help for this data set, it says it's originally obtained from John Woodhouse, is one of these authors. So this comes from the PRIM-H project, which takes its name PRIM from Pictures, Rotation, Isolation, and Masking, first introduced by Tukey and Friedman on the PRIM-9 project. H stands for Harvard, or alternatively Peter Huber. And this is a project that was going on in the late 70s, early 80s. And judging from this paper here, the data actually come from 1964 to 1979, that they seem to match the figure in the paper. And there was also a PRIM-A project, I have to say, from my supervisor, David Andrews at Toronto, which had the same sort of features, again, in the same period, late 70s, early 80s. See more about this quakes on the help in R. So with the quakes there and the just installed packages Loon, you'll be able to reproduce at least the quake analyses. I said this data will be made available in the Loon.data package, which should be coming up later. Okay, that's it for 3D scatterplots in Loon. I hope you found that of some value and that you get to use Loon in your own analyses in the future.